Hello everyone, we're from Group 2 and we will present to you about Warehouse Inventory Management Case Study 4. Before we start, please let us introduce ourselves. My name is Ratu Madina Zela Anifianti with the student ID 240-636-8501 from Industrial Engineering.
Hello, my name is Ranjani Lufina Fatisa Safari with the NPM of 240-644-9962 from Industrial Engineering.
My name is Aifa Shalana Harahap. I'm from Industrial Engineering and my student ID is 240-644-9634.
Hi everyone, my name is Raisa Kirena Maharani and my student ID is 240636852 and 3.
The first thing we need to do is we look into the key issue. Here we're using the SCQ framework. For the situation, we have a large warehouse struggles to manage its inventory efficiently, leading to overstocking and stockouts, increased operational cost. And the complication, the warehouse wants to optimize inventory levels and streamline the restocking process. Where the question is, how can historical sales data be properly managed and the storage capacity be adjusted according to the restock times and seasonal demand fluctuations? After that, we can decide the flow chart, and when we start, we can see the warehouse stores stock according to the average monthly demand, where we use the economic order quantity EOQ 54.8 units. And when the demand increase, we can see the fluctuations and the production activities increase. But if it's out of stock, we need to restock with the reorder point is 133 unit. But if the demand not increased, the production runs as expected. And when the production activities increase but not out of stock, we will back into the production runs as expected. After that, we can make the historical sales data. After the data we conduct, the production had to be evaluated. After it evaluated, the improvement in production quality and product output will also made. And that's the end of the flow chart.
Think about total time complexity in the context of an inventory management system. So let's start with the core logic of the system. There are three main operations. First, sorting item by expiration date with a time complexity of O and log n. Next, iterating through each stock item to check for warning O n. So the last one, calculating EOQ or economic order quantity and the order point, done in constant time O1. When combined, the total time complexity becomes O and log n, which is considered efficient even for a large dataset. Now let's consider the worst case scenario. For example, a large number of stock items. Most items are about to expire within 15 days. Frequent recalculation of EOQ. Even in this situation, since the system doesn't use nest, loops or recursion, the total time complexity remains O and log n. This shows the system is still stable and performs well. If we upgrade the forecasting part using machine learning, such as decision trees, the time complexity might increase to something like O and D, depending on the depth of the model. However, the current system uses a rule-based approach, which keeps the process predictable and reliable.
On this slide, I will explain three important concepts in solving the warehouse inventory management case. The first one is data representation. It helps the system process information efficiently. For example, sales trends can be shown as timelines, product shelf can stored in simple lists, and supplier info organized in tables. This structure makes it easier for algorithms to decide the best way to manage inventory. Next, pattern recognition. Pattern recognition involves identifying demand trends from historical sales data. By recognizing these patterns, the warehouse can predict when demand will increase or drop, so it can restock items at the right time and avoid overstock or stockouts. Lastly, abstraction. Abstraction simplifies the complex real-world warehouse system into key variables like demand trends, storage limits, and supplier lead time. This helps us focus only on the most important data needed for building the computational solution. Together, these three concepts form the foundation for designing form the foundation for designing an efficient and smart inventory system. Thank you.
Here is the Python that we conducted. And here's the result after we run. First up, we have the EO key calculation, which uses simple math formula and runs in constant time, meaning it's always fast no matter the data size, and this is O1. Similarly, the reorder point also uses quick calculation with no loops, so it's also O1. Next, when we prioritize by expiry, we sort items based on their expiry date. This sorting takes a bit more time, so it's O n log n. Formatting a date is just one-time operation, so it's also O1. For stocking list processing, we go through the list to sort it, which is ON. And finally, for seasonal increases or decreases, it's just a simple percentage change, so it's O1. And this big O notation helps us figure out how long these tasks will take and let us improve the efficiency of our process. And that is all from our presentation in our group. Thank you for listening.